So what better way to learn how a CPU works than by emulating one? Which sounds crazy, but I don't know, it sounds like a good idea to me. I think if you write an emulator for a CPU, you do learn, well, you have to learn a lot about how that CPU actually works. So I thought I'm not going to write a whole emulator for a CPU, but I'll start writing one and then we can see how the whole thing works. And I'm going to write a emulator for a really old processor, the 6502. It's like 40 years old now. The reason I'm going to do that is because the 6502 is an incredibly simple 8-bit processor. And although, yes, it's incredibly simple, it does have a lot of the same like principles that it operates on as a modern processor. So a modern processor and the 6502 are, yeah, they're like chalk and cheese, but the principles of how they work are the same. They have memory, they have code, they execute code, and they run through the instructions, they have registers, and so on and so forth. So if you understand how this works, then you will better understand how a modern processor works. And by writing an emulator, you maybe get an idea. So found this website that just goes through all the architecture of the 6502. We'll probably start there. So let's have a look at architecture. So it's a relatively simple 8-bit CPU with a few internal registers, and in fact it's only actually got 3 registers. So a register is just a small area of memory that the computer can access. It can only address 64 kilobytes of memory. Yeah, so that means it's got a 16-bit address bus. So there's 16 pins coming out of the processor that can address the memory. Processor is little endian, which is convenient because I'm little endian as well on my modern PC. So I did a video previously about endianness and why you might care. And so for my case, I'm probably not going to do anything with that because I'm little endian and the 6502 is little endian. So they have something called the zero page in the 6502. And the zero page is just a fancy way of saying the first 256 bytes of memory. And the reason why that's important, as you'll see later on, is that back in the day when memory was very expensive and the computer didn't have very much because of that reason. So the CPU has a bunch of special addressing modes on most of the instructions that allow you to access stuff that's in that first 256 bytes one cycle quicker than you can do with anywhere else. That's actually quite important because it basically means that this first 256 bytes becomes like, it actually behaves like a bunch of registers, like you've got lots of instructions that you can do there. So this was quite an important concept of the 6502. This was one of the things that made this processor like quite fast, is that lots and lots of things could like skip a clock cycle by doing this. And when you didn't have that many clock cycles per tick, well, you had to save as many as you could. The second page of memory, the next 256 bytes, is actually the stack memory. So you've got a 256 byte stack memory, which is amazing to think about, that nowadays stack memory on a modern, just on a single thread of a modern program, is like way more memory than you had on this whole computer. And there's lots of other reserved memory addresses that do various things, and we'll get into some of those because one of them is the reset vector. And that's the place where it reads from initially when the computer is booted up. It had memory, what they call memory mapped I/O. So hardware devices were mapped to regions of the memory in order to exchange data. So that was weird because it meant that even though you had 64K of RAM, certain bits of RAM weren't really accessible because they were mapped to certain hardware things. So that was a bit weird, but that's the way it worked, and it was very simple. And again, this computer was old, or this processor was old. I'm thinking mostly about the Commodore 64, which had this CPU in it, which is the computer I had, but it was in so many computers, like the BBC and loads of others. The Apple had them in Apple II, whatever. We can have a look at what registers the CPU has, and then we need to emulate all of these registers, and there aren't many, so that's quite a good thing. 6502 had a small number of registers, first one being the program counter. Now this is something that you will get on a modern processor, and what that is it's the pointer to the address that the CPU is executing the code for. So whatever address is in there, that's going to be the next instruction that's going to be executed. So that's the first thing we're going to need. So again, straight off the bat, we've initially found a parallel between a modern 50 billion core computer and a 40-year-old CPU. So to start with, I am going to create a little struct. I'm going to call it CPU. And I'm going to start creating these registered. Now the first thing you've got to note here is the program counter is a 16-bit register, because that's the 16 bits is the biggest address we could register, so it's got to register that large. So I'm going to need to define just a couple of things here so I can actually know like what is a 16-bit. I basically need to define a 16-bit and an 8-bit type in here to use. So I'm just going to call one byte, Let's do it like that. So this is where you have to know exactly the size of a certain type on your platform or on your compiler that is a byte. So in my case, I'm going to use unsigned. So we're going to assume that's a byte. And we also need something for the 16-bit one. I'll call that word. So we're going to have byte for 8 bits and word for 16 bits. So I'm just defining my little types for the... let's stick those... Should we stick those in there? So we've got a CPU byte and a CPU word. So we kind of know, like, that's our types for this. So the first thing we need the program counter, and that is a word. So I'll just call that PC. I think it's traditional to call that PC. So we've got a program counter now. So we're already starting to emulate this CPU. We need the stack pointer. Again, the stack pointer is an address. It is the address of the current part of the stack that the program is using. So all modern CPUs have the concept of a stack, which is a small piece of reusable memory. And when you're executing code, you're pushing things onto the stack and you're popping things off the stack. So the stack, in fact, is just a small piece of memory that just gets reused. And again, you can see that even 40 years ago, that was a concept. Okay, there was only a single core, a single thread, and it was only 256 bytes. But the same principles applied back then, just like they do now, that you have the concept of a program counter, and a stack pointer. And now we've got all three registers that the 6502 had. And these are 8-bit registers. So yeah, so you can see like why this really was an 8-bit computer. The registers are 8 bits because it only had an 8-bit data bus. The accumulator, we just traditionally call, I think that's traditionally called A. Index register X, that's traditionally just called X. Oh, we can do this like this. And Y. So those are our registers. Oh, registers. Okay, so program counter. And the next thing is we have processor status. Now this is a bunch of bits. I think this is one single byte. So the processor status is a single byte with a bunch of bits in it that have flags in it that get set depending on what certain instructions happen. And you get the same thing on a modern processor, but different processors have different flags and they're all used for different things. So we've got carry, zero, interrupt disabled, decimal mode, break command, overflow, and negative. And depending on what instruction gets called, these flags will be set or cleared depending on what's going on. So there you go. So overflow flag will be set during arithmetic operations if the result revealed an invalid complement. So you overflowed a sum, and this flag will get set. So we need to define those, and I'm going to define those as we could just do it as processor status like that. Like we could have a byte like that, but because we're going to access all these via bits, I'm just going to do it as a bit field like this. So C++ supports bit fields. C does as well now. So traditionally I think these are just called carry is C, 0 is Z, interrupt disable I'll just call that I, decimal mode D, break command I'll call that B, overflow flag is I think it's traditionally called V, and the negative flag is called N. So so these are our status flags. There we go. So you can see how simple this is. Like literally, I think for the internal data for the CPU, I think this is literally it. Like that's its internal data structure, which is so super simple compared to a modern processor, but it's enough, and it's enough to get code executing. We've got our CPU now. We can put our CPU here, and there you go. We've made our CPU, and it doesn't do anything. It has no code. It has no memory. Now keep in mind that the 6502 can't really operate without memory because it needs the stack pointer to point to somewhere, and it also needs a lot of the instructions need the zero page if you're going to execute anything. To actually execute any code, you at least need the zero page and the stack pointer, and the stack memory, and you'd need some more memory on top of that to actually do anything. So first thing I want to do probably is I want to reset the CPU. Now we don't really know how that's going to work yet, but somehow the CPU needs to get reset into a state like as if you turn the computer on, which this isn't a real computer, but we somehow need to be able to turn this thing on. What I'm going to do is I'm going to initialize some of these values to something like when a 6502 booted up, there is a boot up sequence. I'm not sure if I've got it on here. There's a reset process here. So you'd have this reset vector, which is the address in memory where it would start looking for, and then that would jump to a kernel routine in the ROM, and that would execute some code like this that would do some things, initialize memory and stuff like that. But basically, because we're emulating, we can just fake this for now. So what we could do is we could assume that firstly the program counter, well, we'll initialize that to the value that the reset vector would be, FFFC. Like you can see in here, this is the kind of things, like this is what the C64 would do. It would initialize memory, it would initialize AO, set the IO vectors, more initializing, and then it would actually jump to the basic ROM, and then it would execute the basic ROM, and then the basic would boot up and you'd have your ready prompt. So we're not going to do any of that. We're just going to, like you can see here, it clears the decimal flag. So like that's our D flag. So we would clear that. That would be one thing we'd do on boot up. So I think for now, I'm going to set the stack pointer. I mean, this is really what this boot up sequence here would be doing. The stack pointer is getting set to FF, I believe. What I think is actually happening is it does transfer this value, this FF to the stack, but at some point here, that would be in the zero page. That wouldn't be the first address of the stack. Looks like here the first stack access happens at 100, which is what I would have expected. So I'm just going to, for now, I'm going to initialize my stack pointer to 100, because something like, I mean, I'm not trying to emulate this accurately at the moment. I'm just trying to get something working. And if you want to go through this and accurately emulate what happens here, then you'd have to do all this, and you'd have to load the kernel ROM and do all this stuff. But I just want to get a CPU that boots. It won't necessarily be an actual Commodore 64. It will be a computer that's like a Commodore 64. I think I'll also initialize the A, X, and Y registers to 0. Again, I'm not sure if that's exactly what we'd want to happen, but I'm going to do that anyway. And I'm going to initialize, like it said, it initialized the decimal flag, it cleared the decimal flag. But I think I'm just going to clear all the flags for now. That's going to be my reset routine for now. It's not necessarily accurate, but it's similar to, it's getting my processor into a state where I think I'm ready to execute. One of the things this does do though is it initializes memory. You can see that here. So it jumps to a subroutine that can initialize the memory. So I'm assuming that might actually zero all the memory, which is possible. So what I might do is, that would be the next thing we'd want. We need some memory for this computer. So I'm going to make a struct. I'm going to make a struct called mem, and in here, this is where I need the, actually I'll take these out of here now, because actually the memory needs to access these and the CPU needs to access these. So let's have, this is going to be our data here, for that it's the actual memory, and we need to localize half memory. That needs to be a, let's also define, so I'm just going to define this U32 for, this is kind of like, the byte and the word are for the actual like emulated computer, but the U32 is for me. So I'm just using that there. So const expr, why you got a problem with const expr? Because you're not static. There we go. So we've got a little bit of memory. So we've got some memory. And let's put that here as well. So we've got our memory, we've got our CPU. So the reset probably needs access to the memory as well, because it needs to initialize the memory. So let's pass in the memory to the reset. And in here we will initialize. So we kind of want to do what that thing's doing. I think this is just going to zero this out. But again, it's not very clear. You'd have to go and look at what that kernel routine did on this particular computer. So we're doing a bit of both here. We're trying to emulate the CPU, but we're also maybe emulating slightly what this C64 would have done. There we go. So that's our initialization. Wow, that's really lo-fi, isn't it? So yeah, so we've got a CPU, we've got memory, we've got a CPU, and we've done a reset on it, and technically in a position now where if we started executing, the program counter would want to start reading from this address and start executing the code that's in there. But of course, at the moment, we don't have any way of executing any code in this. So that's all pretty cool so far. So I think next what we want to do then is we actually want a piece of code that can execute an instruction, or we want to execute instructions. So what we want there is we want execute, and it needs to take in the memory, because, well, the instructions come out of memory. If we want to execute instructions, we've got to do them from the memory somehow. So let's execute. In fact, this is going to have exactly the same, well, very similar to this. Execute. So this execute function, at the moment, we've told it to execute, but we haven't told it how much to execute, because we probably want it to execute a certain number of instructions and then maybe stop while we did a redraw of a video graphics or something like that. So the CPU basically has a clock, and the clock ticks, and each cycle or each tick of the clock, the CPU would be able to execute an instruction. It might fetch 1 byte from memory, and then the next execution it might have to fetch another byte, and then it might have to do something else. So what we really want to do here is we want to pass in the number of cycles that we want to execute, the number of like ticks of the clock. So I'm just going to pass in 2 for now, but really what's going to happen is, so we want this to be, it's like the number of ticks. Let's call it, basically what we're going to say is we want to execute instructions out of memory, and we want to execute instructions for this number of ticks. So if we have load accumulator, like you see, I've looked at this one before. This is the one I'm going to do actually. So load and store operations, basically this instruction can take some data and put it into the A register, the accumulator. And if I hit that, loads a byte of memory into the accumulator, setting 0 and negative flags as appropriate. So that's what this does. And you can see where I put the V for the overflow and everything before. So there's all the bits, the status registers that are effective. These are the addressing modes. So these are all the different ways you can call this instruction. And as you can see at the end of the day, what this means is this one instruction that you write in assembly language actually amounts to 1, 2, 3, 4, 5, 6. There's actually 8 different versions of it. And this would be the code that the machine would actually read. So that is the machine code that it would read. This is how many bytes the total instruction needs to take up. So it's 1 byte for the opcode, and there's another byte for the actual data that this one might require. And this is the number of cycles that it takes. So actually we'll call this cycles, because that's what they're calling it here. You can see here that if we want to execute load accumulator in immediate mode, we're going to need 2 cycles to do that. I've actually passed in 2 there. And the reason you can see why is because because this is an 8-bit processor, each time it goes to the access to the 8-bit bus, a cycle needs to happen. So it has to do 1 cycle where it reads the bus, another cycle where it reads the bus. And because this immediate mode one, this load accumulator is 1 byte for the instruction and then another byte for the data that you want to load. Immediate just means like a literal piece of data that you've inlined into the machine code that you want to load into the accumulator. So you'll need a cycle to read the opcode and another cycle to read the immediate value. So it's 2 cycles to read, to load the accumulator, and it needs 2 bytes of code. But basically to execute an instruction, we need to be able to say how many cycles do we want to execute before we stop on our simulated processor. What we need to do then is, let's say while cycles, so we're going to decrement, we're going to say we want to do these number of cycles. We'll keep decrementing these cycles until there's nothing left to do, and then we stop executing and return from this function. We need to fetch the next instruction from memory. So where is the next instruction in memory? It's wherever the program counter told us it was. So you can see now why we need the program counter, because what we want to do is we want to fetch an instruction. And we don't know that it's an instruction, we just want to fetch. When we say fetch, we're going to fetch the next thing that's pointed to by the program counter. That needs to take in the memory, and it also wants to take in the number of cycles, because this fetch is going to take a cycle, like we'll define how many it takes. So this should be the instruction. So we're going to fetch the next instruction. Let's fit that on the screen. There we go. So what we want to do is fetch the next instruction from memory so we know what to execute. So let's write that up here. In fact, let's have the same as this. In this case, actually, because we know we're fetching an instruction, we actually want to fetch a byte, don't we? So let's do fetch. Let's call this fetch byte. Wherever the program counter tells us, we want to take the memory and we want to fetch the next byte from wherever the program counter told us it was, and that would be our data that we got from memory. And then we want to increment the program counter, because every time we do this fetch, the program counter moves on to the next step. That's the whole point of the program counter. We also know from, well, if we looked up the data for this processor, we'd know that the cycles is decremented. Well, we used a cycle to do that. In fact, that needs to be passed in by reference so that we know that when it comes out, it's decremented in number of cycles. And then we can return the data. So that's us fetching 1 byte from memory. I don't think that's going to compile though, because we don't have an operator for that. So let's just put in an operator to get a byte out of memory. So that will just return as, this is basically like a read byte function. And we'd probably assert here, you'd actually put an assert in there to make sure you're accessing the memory correctly. Yeah, so I've just got an easy way of reading a byte there, and that should compile now maybe. Down here, except fetch byte. So the CPU starts up, we reset it, and which includes, in fact, we've reset it, and then we start execute. We've just told it we can execute 2 instructions from memory, and all that does is goes in here, and it fetches bytes, fetches the instruction, and then that will decrement the number of cycles, and we keep doing that till the cycles is done, and then we stop executing. So in reality here, we need to keep executing more and more and more. But for now, I just want to execute 2 clock cycles at the moment. I'm just trying to get this thing like booted up and working. So I wonder if we can get to here without crashing at the moment. So we haven't used this. So it's complaining because I haven't used this variable yet. So I think we can just do this. Yeah, we just cheated it into thinking that it's been referenced. I'm just getting it to compile there. That I'm going to take this out in a minute. So I want to find out if I can get to the end of this without this crashing. And the answer is yes. And we can have a quick look. There's our program counter, our stack pointer has been initialized, and there's all our zeros. So we've got something here, but it doesn't do anything yet. And really, this is where we want to start, like looking at this instruction and seeing if we can actually create an instruction like this and actually run it. So let's do that. So what we want to at least get one of these, like be able to handle one of these instructions. So I'm going to try load accumulator immediate mode, because that's really the simplest one I could probably do. Let's just put this here for now. So these are, opcodes are all bytes on this CPU, and I'll just say it's an instruction, it's load accumulator, and it's immediate mode. And that has a specific opcode here, which is A9. There we go. So now we should be able to switch. So now we should be able to switch on that instruction that we pulled, and actually deal with actually running that instruction. Now all we have to do is like do what it says. Load a byte of memory into the accumulator, setting the 0 and negative flags as appropriate. Well, let's do that then. There's no example of this here, but immediate mode means basically the first byte is the opcode, the second byte is the actual value to load. So what we want to do is we want to fetch another byte from memory. So if we got to here, I'm going to fetch another byte from memory. And this is the value. This is, you can see here that we are expecting that after we got this particular instruction, the next byte is the actual, like, is right there inlined in the machine code, is the next value that we actually want to put into the A register. And then we can just set the A register with this value. So that's most of it, but also setting the 0 and negative flags as appropriate. 0 flag is set if A equals 0, so we can do that. So the 0 flag is Z, and we want to set that if A equals 0, so we do that. And the negative flag set if bit 7 of A is set, so we've got to do that as well. So that's the negative flag. So if A ampersand and bit 7, right, so 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7, bit 7. So if bit 7 of the accumulator is set, then we set the negative flag. So we don't even really have to know what this means. We just need to know that this is what the instruction is supposed to do. So you can see here that this is basically our 2 clock cycles will execute. We'll come in, we say, okay, we want to execute 2 clock cycles. We fetch the instruction. We look at the instruction. If it happens to be one of these, we fetch a byte. That took another clock cycle. And then we set the appropriate things. And then when we came around again to loop this again, the number of cycles will be 0, so we'll break out, and then our program will stop executing. So we've got the world's crappiest 6502 there, is that it's a 6502 and it can only execute one instruction specifically, and that's all it can do. So if we run this, what's really going to happen now is probably nothing, because our memory is just initialized to 0. So we try that in the debug. If this actually compiles, let's go in, we'll execute, and in fact this, so it's going to get the first instruction, it's 0, and it won't execute that. It's going to try for another one, that's also 0, and then it exits. So it didn't do anything. So that's a bit of a shame. So we really need to get a program into memory here that can actually execute something and actually do what we wanted it to do. We should probably also have a default here. Do you need to put break after default? I was never quite sure of that. And now we have basically almost like a debugging thing where we actually we're going to get a printout for if a certain instruction just isn't going to be allowed. We should also really put that assert in, because we're probably going to send the program counter past the end of the stack, past the end of memory, and it's all going to go wrong. But that's if you want to do this properly robust. I'm just like trying to get something working at the moment. After we've reset the memory, let's cheat a little bit. We've reset the CPU. Let's cheat a little bit and let's put an actual program into memory that can execute. So we know we're going to execute from FFFC, which is the reset vector. We've actually got enough room right at the end of memory just to put our little program. So we want an A9, which is going to be our instruction to, it's going to be, in fact, we've actually got a thing for that, haven't we? We're actually going to inline a little program here. So this is quite often something you'll do when you're trying to get something working, is you write a bit of like code that's just inline. This would be loaded from disk or do something else. And then we want to put a, I think that's CPU, isn't it? And then we could do a thing where we load some value. We're going to load hex 42 into memory there. We don't have any way of actually writing into here at the moment. So let's put that in. Right, so it should be. So everyone's back on. There we go. So that will allow us to actually returns as a reference to that part in memory that we can actually write to. So now we've got a little program here. So in effect, if I just breakpoint down here, let's have a look at memory. Is it memory data? Memory data plus FFFC. There it is. There's our little program in memory there, A942. So we've actually hard coded a little program into memory there. So hopefully this is our now, we've actually written machine code in line, virtual machine code in line in this program. So let's just go in now and let's see if we can actually execute that instruction. Remember, I've said I only want to execute 2 cycles, but I already know this only takes 2 cycles. So we're going to go in. We are going to fetch a byte, and that is, where is our, I'm going to add watch there. There it is, A9. It's quite hard to read that. So we did actually fetch, so we're at the right place in memory. And then we're going to fetch a value, and that value is 42. That's the value. We set that into the A register, and then we're going to set these values appropriately. Z should be set if A is 0, which it's not, and if the negative flag is set, then we set negative, and it's not. So we come out of there, and that's our cycle done because we only wanted to do 2. And there you go. There's our CPU, and we loaded our 42 into the A register, and you can see the program counter has moved on, and we're about to go off the end of memory here. So that's going to be the first problem with this, is that we're already about to, we haven't got any way of jumping around in memory. So at the moment, we're just going to keep executing memory till we go off the end, and then we'll just crash, or we'll start overwriting memory in our virtual machine. So that's actually pretty cool so far. So really, when it comes down to writing one of these, programs, one of these emulators for a CPU, I mean, firstly, you're going to have to do a lot more than this, because there's probably like 100 or so instructions, and you've got to do a case for each one of these, and you've got to handle exactly what it does. So there's arithmetic instructions, there's instructions that are jumping around. There's another 7 versions of just this alone. I mean, let's try another one anyway. Let's see if we can do a 0 page. We could do the 0 page one as well, and we could see how that one works. So let's do. So this will be looking at from 0 page. And that is A5. And now we add another case. So what have we got to do for this one? I think for the 0 page one, the next byte, I mean, I'm doing this from memory, but the next byte after the opcode is the address in the 0 page. So this ends up being the same thing to start with, is that we fetch the byte, but this byte is now the 0 page address. But then we want to be able to, we want to use a clock cycle to read that value from memory, but we don't want to use this fetch byte thing, because this is actually incrementing the program counter. So in fact, what we want is a read byte instruction, but the read byte won't affect the program counter, but it will take a clock cycle. So actually, I think what we want is an instruction here that can just, I'm going to call this read byte. So this is the CPU not executing code as such, but just reading a value from memory. And it's going to be very similar to this, except it doesn't increment the program counter, because we're not executing a piece of code here. We're just actually reading a piece of memory. So this ends up being pretty much the same. So let's go in down here. So we got our 0 page address. Now we want to read the byte from the 0 page address from memory. And that is going to be, in fact, that can go straight into the A register. So you can see why that took 3 clock cycles now. So this 0 page takes 3 clock cycles, because it's 1 clock cycle to fetch the instruction, a clock cycle to fetch the immediate value, to fetch the 0 page address that's stored in the machine code. And then there is the read byte function, which takes another clock cycle to just get that into the A register. And then the next part, again, this bit's always the same. So we always do this bit afterwards. So this is probably where we want to extract this, setting the 0 flag and the negative flag out into a function. So LDA. So every time we execute an LDA instruction, we're just going to do that afterwards. What's wrong with you? 0 page address needs to take, got this wrong. So it needs to take the number of cycles. There we go. So yeah, so this read byte needs to take the cycles, the address, and the memory into account here. So we actually need, Yeah, so it needs to take the cycles, the address, and the memory. Had that wrong before. There we go. So this read one byte, yeah, needs the cycles, it needs the, oh, and the address is not the program count. I had that totally wrong. It's the address there. There we go. That's better. That makes total more sense. So, in effect, is that correct? That our load accumulator from the zero page can now fetch the byte, read the byte, and then sets the status register. Are we compiling? Yes, we are. And let's change our little program to load from the zero page. Is that what I called it? We're going to load from the zero page address 42. And what we'll actually do is at the zero page address 42, we're actually going to stick an actual piece of data in, and this data will be 84. So in effect, what this should do is take the value 84 and put it into the accumulator. So we're going to need to execute 3 cycles to get this one working. So let's see if that works. So first cycle, we get our instruction, which is A5, that's the correct instruction. So it's going to switch to the correct one here. We are going to load the zero page address, which is 42, and then we're going to read from the zero page address from that memory and load it into the A register, and there it is, the value 84. Then we set our flags and we come out, and there we have it, and 84 got into our A register. So we've now implemented 2 instructions. We've got load address immediate and load address from the zero page. So you can see how this goes now, is that I'm just implementing one. I think there's 22 or something instructions in the 6502, but with all the addressing modes, there's actually quite a lot more basically. So there's another one here. There's in fact, we could have looked at the zero page thing there. Yeah, so this website actually tells you about how these kind of things work. So Zero Page X. So there's another one here. The address to be accessed in instruction is indexed using the zero page by taking the 8-bit zero page address from the instruction and adding the current value of the X register to it. So there we go. So it actually tells you how to do that. So let's do that one as well, because that can be done. So zero page X, zero page X, which is B5. It's 4 cycles. Now you can see 4 minutes. Obviously it's taking 4 operations to actually do it. So this one is exactly the same as the X register to this value. So we get the address of the zero page in there, and then we get the add X to the address value. By taking the zero page address instruction and current value address. Yeah, so it's the address. So yeah, that's the address and then loading address. So zero page address is that, and then take the zero page address and add the X register. Now remember, this takes a clock cycle. So yeah, cycle. So we take a clock cycle to do this operation, and then do the same thing we did afterwards on this one, which is we read by zero page adjusted by X offset. This instruction incredibly similar, except it's offset by 1. So you can see why that needs 4 clock cycles now. We need 1 to fetch the instruction, the opcode, 1 to fetch the zero page address, 1 to increment with add the X value onto it, and another one to actually read the byte. So that's our 4 clock cycles. So this is all starting to make loads of sense, and you can also see that Y, is there a zero page Y? There is no zero page Y. There's only zero page X on this one. And then you can go through and like do all these, basically load X register, load Y register, and so on and so forth. You could probably find a lot of repeated code in here and start actually, like I did with this LDA set stars. There's probably like loads of things here where you can keep doing this, but essentially that's how you start writing a processor. The only other thing you've got to do then is actually load a program into memory. I suppose one of the other instructions that we're going to need before we really do anything, in fact it was right there, is JSR, jump to subroutine. Jump to subroutine, we can't actually move around the program counter. So that would be another one we'd need. We'd need to be able to take the current program counter. We want to be able to go to an absolute address in memory, push things onto the stack, pop things off the stack, so on and so forth. Yeah, JSR instruction pushes the address -1 of the return point onto the stack and then sets the program counter to the target memory address. Maybe we should have a go at that one, because that way we'll actually have to use the stack, and we'll actually have to use a 16-bit address as well. Yeah, okay, so firstly, this is absolute addressing mode, which we didn't do before, but absolute addressing mode, instructions using the absolute addressing mode contain a full 16-bit address to identify the target location. In fact, their example there is, one of them is JSR. So the first thing we're going to need to do is read a 16-bit address from the program. So we need a fetch word That's what we're going to need. So we want fetch word, and we want to fetch it from where the program counter is. So it's quite similar. It's going to be quite similar to this, except basically this is the bit where we now need to know that 6502 is little endian. So that means that the first byte that we read is going to be the least significant byte of the data. So actually we can just read the first byte and stick it in there and decrement a cycle. And for the second byte, that's going to be the high byte. It's going to be something very similar. It's going to be very similar actually. We're going to read again, except this time we are going to shift it up by 8 bytes, and we're going to OR it. There we go. So in fact what we can do here is we can turn this into just cycles plus equals 2. Rather than just having 2 minus minuses, because we don't really care too much until that's done at the end. 65.2 is little endian, my platform is little endian, and this is where that if you wanted to handle endianness, you would have to swap bytes here. So you would probably have something like if platform be endian, then you would swap bytes in word data. Yeah, so that would be how you'd handle if you wanted your emulator to compile on any platform. You'd have to know whether your platform is big endian or not, and you'd have to swap them. I'm not going to bother here because I'm little endian and the 6502 is little endian, so actually this all works out in the wash. But again, what I'm doing here is I'm just I'm reading it out, and then I'm making the assumption that my platform is little endian, and then I'm just swapping at the other end. So the other way of doing it would be to just do this in the other order and write the code differently. But I think this way is nicer because you always handle it in one way and then just swap it. If you're big endian, I don't know, that might be good, it might be bad, but I'm not going to bother handling it here. So we are going to implement our thing. Now we can fetch a word. So we fetched our instruction, and we are going to fetch the word. So that's the jump address. Subroutine address is going to be this. Word from and push the address -1 of the return point onto the stack. Okay. So this is where we need our stack pointer. So we've got our stack pointer here, and we've got our memory. Push the instruction pushes the address -1 of the return point. Yeah, so the return point is going to be where we are now, -1. And I suppose the reason for that is that when you execute the last instruction at the end, the program counter will have to read this back off the stack and then increment the program counter +1. So we're actually going to, so this is what it's telling us to do, is push the return point, which is where the program counter is right now. Remember the cycles, that takes a cycle to do that. And then set the program counter to the target memory address. So then the program counter becomes the subroutine address, and that takes another cycle. And it doesn't affect any flags. And there we go. And I think that's our 6 cycles, is that 1 cycle to get the instruction, 2 cycles to get the address from memory, that's 3, another cycle to set the oh no, actually there's going to need to be 2 cycles for this. Yeah, because that's only 5. Actually, we've got this wrong, because now what we want to be able to do, this, I've actually only written 1 byte, and here I need to write 2 bytes. So this is the next thing I'm going to need. I need to be able to write a word. I want to be able to write a word in here. Address. Okay, and so remember again, we are which means so the bytes first, and just do actually. The least significant byte goes in first, the most significant byte goes in second, and we can write a word in there. Why? What's wrong with that? What is wrong with you? Oh, because it needs to be. Is there anything wrong with that? Oh, we can't have data. There we go. So now we can write now we can write 2 bytes. While we're at it, why don't we take in the cycles for that as well? And we will take 2 cycles off because we took 1 cycle to do that and 1 cycle to do that. I don't know what order to put these in. This is going to be a very confusing function to call. Here we go. So the return address -1, and we don't need that anymore because we're subtracting our cycles. We do the value, the address, which is the stack pointer, and the number of cycles that this takes, so we can increment it. Did we actually take that in by value? We didn't. Whoops. Cycles has to be by value because we're changing it. Now we're doing what it says, I think. Yeah. Read the instruction, 1 cycle. Fetch the address that we want to go to. That takes 2 cycles. Then we want to write the address -1 of the return point, which is currently the program counter -1, onto the stack. It takes another 2 cycles. That's 5. And then lastly, move the program counter on to where we want to jump to. So that is our jump to subroutine function. And there's why it takes 6 cycles. And you can see why it takes 3 bytes, because we actually read 3 bytes. So this all kind of comes out in the wash. This is really good. And maybe we should see if we can actually do a JSR and the immediate rest of the routine. But we can hack the program now. CDE. So remember, little bit is first. In fact, let's just jump to, let's not jump to 0, 0. Let's jump to 42, 42. So in effect, this should read the reset vector, which can have a jump to subroutine, which is going to take us to 42, 42. And it's also going to push the return value onto the stack. And then in effect, if we actually did put something at 42, 42, well, if this works, this will be awesome. We'll put in a load immediate function. And we're going to load the value 84 into the A register. And what do we need to do this? 9 instructions to do this. So in effect, what this will do is it'll start the program and we'll end up with just 84 in the A register. And I'm going to run it and hope for the best. Here goes nothing. And what did we get? We got it. We got 84 in the A register. And we didn't really return from our subroutine because we haven't written that yet. But that's pretty cool. We actually got a program that can actually branch. Well, not really branch, but it can jump around in memory now. Hence the random access part of it. So I actually think, like, considering the amount of time this is taking me, that's actually pretty cool that I've got this much actual, like, of an emulated CPU running in this amount of time. You can see why people write these, because I suppose this is kind of like fun, if you know what I mean, like working out how a CPU works and how can you actually emulate one. But I'm actually quite happy with that. So I'm going to leave it there, but you could see that if you wanted to carry this on, you just got to keep putting these instructions in and getting them to work, and you've got to do all the adds with carries and all that kind of nonsense. So I'm not going to do all that here because it's just a lot of work, but this is the beginnings of an incredibly simple CPU. And the other cool thing to notice is, have you noticed how the entire memory and the CPU, this entire program didn't allocate any heap memory. It's all actually on the stack in my on my machine. So the memory is on the stack and the CPU is all on the stack. So the entire thing is totally like, it didn't allocate any memory to access the whole thing. The whole computer can run on there. You can also see that this is one of the other points about this, is that when you do actually create because you'd have to, like, if you want to do this properly, you'd have to create debugging and all kinds of nonsense. When you actually create one of these emulated CPUs, that once you've emulated the whole CPU, you'll realize that you can't actually do anything with this. The CPU can, it can read and write its memory, and it can read and write registers and so on and so forth. But until you put some input and output on it, you will never be able to see any output from this CPU. So really, you can see why a CPU on its own can't do anything. It's the central processing unit, but you can't see anything, you can't hear anything, it can't write to any serial buses. It can just affect the memory that's in the computer. So really what you need to make a full emulated machine is you need to start interfacing with, for instance, a video chip. And that's why you can see, like, when you get a computer, it's the other chips around the CPU that are really making the computer work. So if you put a video chip in here, that'd have some memory and some registers. If the CPU could actually access those memories and registers, it could then start displaying things onto the screen. But this emulated CPU here can't do that. But you'd still have to write all this to get to the point where you were actually showing stuff on the screen. So this can't write to a terminal, it can't do anything. But in effect, it's starting to work. You could also see how maybe if you were writing your own scripting language, that this is kind of how a scripting language would work. If you get a scripting language and you could compile it into a bunch of very simple instructions, they could be executed like this, and you could basically have a compiled language. The problem you'd get then is that really all the work's in the compiler. It's not actually in the machine itself. It's in the compiler, and how does this interact with the rest of the program? So I hope you learned something there about how an actual CPU might work, and how you might emulate one, and how you might go through all these and start implementing all these. And you can see none of them would be very hard to implement. Subtract with carry, decimal flags, store accumulator. Yeah, we did that. Did we do store accumulator? No, we did load accumulator. So this one takes the accumulator and puts it back into memory, and that's like the opposite. So very cool. I hope you learned something from that, because I'll put this on GitHub, and maybe we'll continue it at some point and start adding more and more stuff to it. But this is super, super basic. But you could see that in a day or two, well, maybe in less actually, you'd probably be able to get a whole machine working. And also shows where you'd need to do a lot of testing to make sure this thing's actually working. You could write a test for each one of these instructions because it's so simple. And you could get a fully working 5502, a 40-year-old processor emulated on a 0-year-old processor.